along the lines of, I am 95% confident that mu is within about 2 standard deviations of y bar, okay? And this is standard deviations of the sampling distribution. Not sigmas themselves. Does that feel okay? All right. And technically, if you look at your z table, your normal distribution table, if I wanted to get the middle 95%, have 0.95 here and have 0.025 out there and 0.025 over here, my z's are technically not at 2 and negative 2, it's technically at negative 1.96. And z equals positive 1.96. Alright? So it's we say about 2, but it's actually 1.96. So if I see y bar here, so if we have y bar, we can say something like I am 95% confident that mu is between, and I'm going to do y bar minus 1.96 times the standard deviation, which is sigma over the square root of n, and y bar plus 1.96 times sigma over the square root of n. Does that sound reasonable to you guys? Right. Have I lost anyone here? Or are we all following this okay? Okay. And we're able to say this because we know that y bar comes from a sampling distribution, and that sampling distribution follows the normal distribution. Alright. There's one problem here though. Can you guys see the problem? I'll let you guys finish writing all of this. The problem is, we don't know what sigma is. What is sigma? Sigma represents the standard deviation of the population. Okay. Can you imagine a situation where you don't know the mean of the population, but you know the standard deviation of the population? Probably not. Probably not, okay? There might be some rare circumstance where that happens. But in general, if you don't know the mean of the population, you're probably not going to know the standard deviation of the population. Okay? So this quantity is actually unknown to us, sigma. We don't know what sigma is, so we have no idea what kind of standard deviation we're dealing with. So what should we do? We don't know the standard deviation of the population. Do we have any idea what the standard deviation of the population is like? Is there any way for us to guess? What do you think?
Well, since we know the kind of the shape of the curve by how the percentages of, like, this kind of thing's terrible, but we know the distance percentages, can't we use that somehow to figure out?
It still requires us to make assumptions about the standard deviation of the population. You're right, we can say 68% of the time, we're within one standard deviation of the mean, but we still don't know what one standard deviation is. So, is there any way, how can we estimate the standard deviation of the population?
What's the population size?
No, the population size.
Range?
Alright, so let's say, let's say we go to a new country, and we say, or I don't know, let's say we discover some land of uncontacted peoples, right? But they're friendly. But we want to understand something about them. So let's just start off with something simple. What's the average height of the people that we just met? Well, we might take a random sample of maybe 20 people. And we can calculate the average height of these 20 people that we selected. But we still have no idea what the standard deviation is. So we have no idea what the population mean is. We have no idea what the population standard deviation is. We took a random sample of 20 people and we can calculate a sample mean. The sample mean serves, for better or worse, an estimate of the population mean. Okay, and we're going to create some range to give us some leeway here. What about the standard deviation? Of the sample. So I can just take the standard deviation of the sample itself, and that might serve as a rough estimate of the population standard deviation. Does that sound reasonable? Okay, well it is. So we don't know what the population standard deviation is, but we can take the sample standard deviation. So we have a sample of some values. We can take the standard deviation of that and use that as a rough guess for the population standard deviation. Okay. But again, anytime we're taking using values from a sample, we have no idea if that value is bigger or smaller than the actual population standard deviation. So I've taken a random sample and I'm calculating the standard deviation of this random sample. I don't know if that standard deviation I just calculated is too big or too small. And so because of this extra uncertainty that's going into it, I'm going to compensate for that. I'm going to compensate by altering this number 1.96. So if I want to remain 95% confident that my interval catches the population mean, would I compensate by making 1.96 bigger or 1.96 smaller if I'm using an unknown rough estimate guide of the standard deviation?
Bigger.
I'd make it bigger. Okay. So we're adding another layer of uncertainty, and so to compensate for that, we're going to alter this number 1.96. Okay. So let me just write all this. But we have a problem. We do not know what sigma is. So we will use S, the standard deviation of the sample, problem, we don't know what sigma is, so we will use S, the standard deviation of the sample, as an estimate of sigma. But to compensate for this additional uncertainty, we will change 1.96 to something bigger. So now I have y bar minus, instead of 1.96, I'm going to put in the symbol t star as the number that I'm going to use that's a little bit bigger than 1.96. Multiplied by s over the square root of n. Okay. So we're going to say I am confident that mu is between y bar minus this and y bar plus t star times s over the square root of n. Okay? And sometimes we combine the plus and minus and we just say y bar plus or minus t star s over the square root of n. Okay, so this is our confidence interval, abbreviated CI, confidence interval for mu. Is y bar plus or minus t star times s over the square root of n. So let's further refine this idea of using a number bigger than 1.96. Okay. The reason why we're using a number bigger than 1.96 is because we said there's some extra uncertainty of using S as an estimate for sigma. If we knew what sigma was, sure, we would use 1.96. But we don't, so we're using our sample standard deviation as an estimate. How good is our estimate of sigma? If I take a huge sample, if I have a sample of 1,000 people, and I calculate the standard deviation of that sample, do you think that would be a pretty good or pretty bad estimate of the population standard deviation? I would say pretty good. Okay, if I got 1,000 people, I'd say it's going to be a pretty good estimate of the population standard deviation. It's not going to be exact, but it's going to be pretty close. On the other hand, if I take a really small sample, maybe a sample of 5 people, is that going to be a good or bad estimate of the standard deviation?
Yeah.
Okay? There's certainly a lot more unpredictability about it. Okay? So that's accounted for when we select t. Okay, so when we select this value t star, we're going to take into account the size of the sample. Okay? And this is all, we use t star because it's coming from what we call the t distribution, the student's t distribution, which is based off of the normal distribution, but it's just made fatter. Okay, it's made, the distribution is made wider, and how much wider depends on what we call the degrees of freedom. Okay, so the sample size plays into what we call degrees of freedom, or I'm just going to call df, and df is equal to n minus 1. Okay. Degrees of freedom is this idea that you are free to change n minus 1 things as long as so like we could play a game and I could say I can let you pick any set of numbers and I can make, as long as I get to pick one number, I can make sure that the average of all the numbers we select is 10. Okay, so if I play the game with 5 people, the first 4 people can pick whatever numbers they want, but as long as I can pick that 5th number, I can make sure the average of the 5 numbers is 10. Does that sound right? Okay, because you can all pick like crazy numbers, and I just have to make sure, whatever numbers you pick, I just have to make sure that all 5 numbers add up to 50. Okay, so that number could be, the number I pick can be negative or positive, whatever it is. As long as all 5 numbers add up to 50, the average is going to be 10. Okay, so 4 numbers are free to have freedom, quote unquote, and then the one number is locked in. Okay, so that's where we get this notion of degrees of freedom, n minus 1. And it plays in with our sample size. And this is how we select our t. Okay, so if you look at your reference tables, flip to the next page, not the normal table, but you'll see table 4, critical values of students' t distribution. Okay. And look at the bottom where it says confidence level. So we can make 95% confidence at level intervals, we can make 99% confidence intervals, we can make 80% confidence intervals, and all of these other things. Okay, we can choose different confidence interval levels. So at 95% confidence, you can see if I had infinity degrees of freedom, the value I would use at the intersection of infinity at the very bottom row and 95% is 1.96. Okay, see that? Okay. But for anything less than infinity, you see that we use a number slightly bigger than 1.96. Okay? Until you get to the top where you only have 1 degree of freedom and we're using a ridiculously large 12.7. Okay? But most of the other numbers is only just a little bit bigger than 95%. So for example, if you have 9 degrees of freedom, you use 2.262 rather than 1.96. Okay, so we use, so look up T star in the T table. Okay, so let's try making a confidence interval. Okay, so let's say we take a random sample of 10 people. Say the mean height of these 10 people is 66 inches and has standard deviation equal to 3.3 inches. Make a 95% confidence interval population mean for the population mean height mu. Okay, try that out. Okay, how are we doing? Do we get a confidence interval? Yeah. Alright, so my confidence interval would be 66 plus or minus t star. What is the t star I would use?
2.262.
2.262. I've got 9 degrees of freedom, 95% confidence. 2.262 times s. What's s? 3.3, my sample standard deviation, divided by the square root of 10. And now it's just punching this into the calculator and getting a result. I don't know what I did with my calculator, actually. Here we are. So I have 66 plus or minus 2.36. And so my confidence interval, I would say, goes from 63.64 to 68.36. And I would say I'm 95% confident that the mean height of, or the population mean height is between 63.64 and 68.36. Okay. So I'm 95% confident that the population mean height is between 63.64 and 68.36. How does that feel? Feels okay? So if you take a sample of 10 people, and the mean height of those 10 people is 66 inches, and the standard deviation is 3.3 inches, would we say we have evidence that the mean height is not 67 inches? Do we have evidence that the mean height is not 67 inches?
No,
No, why not?
it's probably in there.
Yeah, because 67 is within my interval. Okay? But if I said, do we have evidence that the mean is not 69 inches?
Support.
Yeah, okay, our data at least supports that. Is it possible that the mean is 69 inches? It's possible, but then what happened? Why does my confidence interval go from 63.64 to 68.36?
Your sample is skewed.
Yeah, so it's possible that the true mean is actually 69, but if the true mean was 69, what happened was that because I took a random sample and the gods of randomness played a trick on me and gave me a sample of 10 people that basically led me astray, okay? That my sample of 10 people was a little bit weird and led me to believe that the mu is between this and this, where in fact the mean was actually outside of that, okay? But we're 95% confident that mu is between here and here. Okay. So if somebody says, do you have evidence? Do we have evidence that it's not 69? We would say, yeah. We have evidence that it's not 69. But is it possible that it's 69? It is possible. It just means that that our data would have to be something unusual for it to actually be outside of our range here. Okay. Does that kind of make sense? Should I write all of these things down? No? Okay. All right. Something to be careful. Do not say there is a 95% probability that mu is between 63.64 and 68.36. Okay? So we can say I'm 95% confident that mu is between here and here, but do not say there's a 95% probability that mu is between there and there. What's the distinction?
It's an approximation.
It's not that it's an approximation. Okay, so let's let me just try a little trick here. Not a trick. Okay, so let's say I have a coin. What's the if I flip this coin, what's the probability that this coin will land heads? 0.5. Okay. Oops. All right. What is the probability that the coin has landed heads?
0.5.
Watch what I do here. What is the probability that the coin has landed heads?
0.5.
So it was a trick question because it does not make sense to talk about the probability of how the coin has landed, because there's no uncertainty of the state of this coin. The coin either has landed heads or it has not landed heads. Okay? You don't know. You don't know if it landed heads or not. Okay? But it does not make sense to say the probability that the coin has landed heads is 0.5, because it either has or it hasn't. So at this point, all you can say is I am 50% confident that the coin has landed heads. Is the distinction there clear? Okay? So we only make statements of probability for things that have uncertainty. Okay? We only talk about probabilities when there's uncertainty. In the case of mu, the population mean mu, there is no uncertainty. The mean of the population is some value. It's some value, we don't know what it is, but it's some value and it's fixed. Okay? The mean of the population doesn't care what my sample looks like, it doesn't care what my confidence interval looks like, the mean of the population is some value mu. So there's no uncertainty about it. So it does not make sense to say there is a 95% probability that mu is between here and here. There's no uncertainty about mu. It's either inside my interval or it's not. I don't know the value of mu, so all I can say is that I'm 95% confident that mu is between here and here. Okay? Just like the coin, it has landed. It doesn't make sense to say there's a 50% probability that it landed heads. You don't know how it has landed, but there's no uncertainty. Okay? So all you can say is I'm 50% confident that it has landed heads. It landed tails, by the way. Okay? So do not say there's a 95% probability. Will you hate me if I did some stuff on R? Yes? Okay. Well, alright, maybe I won't then. You scared me away from doing R. I was going to illustrate this concept of 95%, okay? Versus, I could make a 90% confidence interval and what would happen? if I chose to make a 90% confidence interval, what would change?
T-value.
Just this, just the t-value. My mu, not my mu, my y bar is still 66. My s over the square root of n. Oh, by the way, s over the square root of n, this is known as the standard error. Sorry, I should have mentioned that earlier. It's known as the standard error. That's just what we call it. The standard error is, I guess, our estimate of the standard deviation of the sampling distribution. Okay, because the standard deviation of the sampling distribution is sigma over the square root of n. When we are estimating that with s over the square root of n, that's our standard error. So our standard error remains the same, our y bar remains the same. If I change it from 95% confidence to 90% confidence, the only thing that changes is t. Does t get bigger or smaller if I decrease my confidence?
Smaller.
It gets smaller. Why is it getting smaller?
Because you're shrinking the window.
Because I'm giving up confidence here, all right? So, imagine that there is someone running away from the police, and they see him go into a neighborhood. And so they want to block off the neighborhood and do a sweep and make sure to try to catch this guy. All right? They could block off a huge area and be very confident that this runaway is somewhere in here. Okay? But they're having a huge search zone has its problems. So they could shrink the search zone, but what they're giving up is quote unquote confidence that the search zone contains the runaway. Okay, so you know, a couple years ago, you know, the Boston bomber, marathon bomber, he like hid in a boat or something, and they had a search zone. And that search zone, they searched the area, they didn't find the guy because he was just outside of that search zone, okay? So there's, you know, a balance between how big of an area or how large of an interval you want versus how confident you want to be, okay? So if you want to be more confident, you're going to have to search a larger area or have a wider interval. If you're willing to give up confidence, you can have a smaller interval. You know, if I wanted to be 100% confident about the location of mean, I would have to say, I'm 100% confident that mu is between negative infinity and positive infinity. Okay, that's the only way I can be 100% confident about any value mu. But that's not very useful, so I can give up some confidence and have, you know, an interval. Someone might say, to tell me that mu is between 63 and 68 inches, that's a pretty large spread. It's not very useful. And they might have, there might be some validity to that, okay? So we can have a smaller interval, but we're giving up confidence. Okay. Make sure you write that somewhere in your notes, okay? So the trade-off, less confidence, you will have a smaller interval. If you want more confidence, you're gonna need a larger interval. Either that or you need to collect more data. And by collecting more data, you're shrinking your standard error. But that's what we have. Okay, so I won't do the illustration on R, but instead I'll just say, what does it mean to be 95% confident? The idea of 95% confidence is that if I were to repeat this process many times, take a whole bunch of different samples of size 10, and for each of those samples create a 95% confidence interval. Okay. And let's say I knew the true value of mu. Okay. So if I know the true value of mu, and I just go through this process, of taking a whole bunch of samples and creating 95% confidence intervals, then according to the rules of statistics and all of this, 95% of those confidence intervals will contain the true value of mu. Okay, so mu is some fixed value, and if I take a whole bunch of samples and I make a bunch of 95% confidence intervals, about 95% of those confidence intervals will contain the true value of mu. Some will not, because the samples were unusual. But 95% of the samples will produce a confidence interval that contains the true value of mu. And I could illustrate that with R, do a bunch of simulations, and you would see it. But you can just take my word for it. And we'll just end class a few minutes early.